My name is Dimitris Mouris, and today I will present to you my joint work with Charles Gerd and Nektarios Tsoutsos on new insights into fully homomorphic encryption libraries via standardized benchmarks. So we talked a lot about homomorphic encryption, but let me go over it one more time. Homomorphic encryption is a very cool technology that allows computing directly on encrypted data. And to visualize this, we have a client and a server. The client has some data. They can encrypt it locally using homomorphic encryption, upload it to the server, to a cloud service provider, which can run an encrypted computation without seeing anything about the data, and send back an encrypted result. Now, only the client who has the secret key can decrypt and learn the final result. There are many applications that can harness the power of homomorphic encryption, such as privacy-preserved machine learning, where we can do encrypted inference. For example, a user has an image, and they want to learn an encrypted classification, but they don't want to reveal that image. Also, we can do encrypted sorting or encrypted search, where the user wants to keep a keyword private and search inside a large text file or a database. There are many homomorphic encryption libraries and schemes that are actively being developed, and each scheme has its own benefits. And also, each library expresses its own API, which leads us to the question, how do you choose which HE library, homomorphic encryption library, to use for a given application? A few more details about homomorphic encryption. We have different types and schemes. Regarding the types, we can have partial homomorphic encryption that allows either addition or multiplication to be performed on the encrypted data. Then we have level homomorphic encryption that allows for a limited number of additions and multiplications. And finally, we have fully homomorphic encryption that allows for an unlimited number of additions and multiplications, with the only caveat that in order to keep going, we need to do a special operation called bootstrapping. So in this work, we focus on the latter two technologies or variants, the level and the fully homomorphic encryption. Regarding the schemes, we have binary schemes, such as CGGI. Most of you know it as TFHE, that encrypt each bit of a word, of a plaintext word, separately. And in order to do an algorithm on this scheme, we have to compose it as a Boolean circuit. Now, binary schemes have very fast bootstrapping, but unfortunately, they have low throughput. On the contrary, we have integer schemes, such as BGV and BFV, that they can directly encrypt an integer modular prime. And because of that, they have very fast addition and multiplication, and they correspond to plaintext addition and multiplication. And however, we have very slow bootstrapping compared to the binary schemes, but very high throughput because they allow SIMD-like operations, where each ciphertext can include multiple integers. And when we do an operation between two ciphertexts, this corresponds to a vectorized operation. This is called batching. Finally, we have floating point schemes, the most popular being CKKS, that encrypt floating point numbers directly, but up to a certain precision. And floating point schemes share many similar details with integer-based schemes, and they also have slow bootstrapping, but they can do batching or packing, and thus they have very high throughput. Now, we have many homomorphic encryption libraries that implement some variants of these schemes, and each library has different optimizations, and they also expose a different API, and they are also written in different languages. And all this leads us back to our original question, how do you choose where you get started with homomorphic encryption, which library to use for your given application? So to this end, we have created a framework that's called T2 to allow for easy comparison between libraries and schemes. T2 is composed by a high-level language. It's our custom language, which we call T2 DSL, and a compiler from the T2 DSL to the most popular homomorphic encryption libraries and schemes. Finally, we proposed different benchmarks, and we implemented them in our high-level language, and we use our compiler to compare these libraries and schemes. So a few things about the language. It's strongly typed, and it has, for the plaintext types, we have integers and doubles, and the corresponding array types. And we can do mixed operations between plaintext and ciphertext types. Then when we deal with integer and floating point ciphertext, we have encrypted integers, encrypted doubles, and arrays. And as we mentioned before, when we have integers and floating point schemes, we have very cheap and fast arithmetic operations, additions and multiplications. But comparisons are almost never used because they're very expensive, and in order to do them, we have to do some polynomial approximations. So our compiler and the language support doing comparisons, but being very slow because we use these polynomial approximations. Finally, when we have binary ciphertext, we can only use encrypted integers and arrays, and the arithmetic operations now need to be composed as Boolean circuits. For example, in order to do an addition between two ciphertexts, we need to have a binary adder. And finally, for comparisons, we have comparator circuits. This is an example of how the language looks like. I don't want you to focus on the code, but the idea is that we have high-level code, and with the same high-level code, the T2 DSL, we can get different backends just by running our compiler. And all these come from the same high-level code. Next, we propose a benchmark suite in order to evaluate all these different libraries. And we distinguish 3 classes of benchmarks, namely arithmetic, bitwise, and relational. The arithmetic benchmarks are benchmarks that are mostly composed by multiplications and additions. Then the bitwise are benchmarks that have many bitwise operations, logical gates and shifts. And finally, the relational are benchmarks that have comparisons. All right, so logistic regression is an arithmetic-heavy benchmark, and because the schemes and the libraries that are binary and they don't support arithmetic operations natively, such as TF-8C in this case, you see this big difference between the schemes and the libraries that support arithmetic operations versus the binary scheme. Moving on to another arithmetic benchmark, the neural network. In this case, we didn't even plot TF-8C because it was very slow. But we have some interesting results. And we see some differences between the libraries. So all these are in the arithmetic domain, integer or floating point. And in the green bar, you can see SEAL, that's fastest for the integer domain, whereas HELIB is fastest for the floating point domain by a huge margin. Finally, to do some justice to TF-8C, we have a bitwise benchmark. And the CRC8, you can see that TF-8C is significantly faster, and the other libraries are approximately the same. Whereas in the CRC32, which is a deeper circuit, we can see that TF-8C, highlighted in blue here, is significantly faster from HELIB, which is the only other library that supported bootstrapping at the time, and was able to finish executing this benchmark. Because these benchmarks are, we use arithmetic schemes for HELIB, for instance, to run them as bitwise and run the bitwise benchmarks. And we have way more experiments in the paper. So the lessons that we learned from this study, we have a clear winner for the binary domain. And this is TF-8C. It has the smallest ciphertext sizes, and it has very fast bootstrapping, but it does not have the batching operation, so it has very low throughput. Next, we observe that Palisade has the fastest primitive operations. So we have a table in the paper that we just compare how fast a multiple multiplications are or multiple additions. And Palisade was the fastest in this case, both for integer and floating point. However, when we plugged Palisade and the other libraries into benchmarks, Palisade was not always the fastest, which was interesting. Next, some libraries allow you to give you very much enough freedom with the parameters, whereas other libraries restrict you. And this directly affects how the noise grows and also how fast its execution is. Lastly, we observe that HELIB is very fast for the floating point, and this is mostly attributed to the fact that it has automatic and very fast rescaling operations. And the takeaway from this slide and this talk in general I want to be that you don't have to trust us for these results. Our library and our code are open source. So, and also this varies from application to application. So you can implement your own code in high-level language, and you can easily compare the different implementations. To summarize, we created a benchmark suite for encrypted computation and a universal compiler to translate these benchmarks to the different backends and schemes. And T2 enhances the usability given the high-level language and the compiler, and it allows users to find which is the best application and scheme given their application needs. Yep. All right, you can find our paper and our code in the following links. Thanks for your attention. I realized that I went very fast, so I think we have time for many questions.
Yeah, we do. We have 5 minutes for questions. So we have a couple in the chat. Here's one from Anders Delskov. He asks, can this framework be used to give the user an idea about which scheme to use for a given program without having to run the program with all the schemes to figure out which is the most efficient?
Can you slow down the second part? I got the first part, I lost in the second.
So can you figure out which scheme to use without having to run the program with all the schemes to figure out which one is the most efficient?
Okay, great question. No, actually, so you can see from the code size, we observe that of course you have to compile them, but in order to avoid running them, you can, if you want to spend time and observe like the compiled binaries or the compiled source files, you can get an idea of how slow or fast like its scheme and library may be. Another thing that I didn't mention here is that, given the same code, when you have an integer scheme, for example, you can pass a bit size, and then we can emulate a binary scheme. This is to do the bitwise benchmarks. Otherwise, the circuits would be too noisy to do the bitwise benchmarks. So in that sense, you have like an idea of how fast or slow something would be. Like, if your benchmark is very heavy on integer multiplications and additions, then you know that you don't want to go with TFHE, for instance. But in order to, we found some interesting results. Like in some cases, things did not go as we expected. And I think, I don't have an answer in the sense, I don't know like which library would be like the fastest, but I think T2 will enable you to figure that out for an application.
Okay, another question is from Anselm Tuino, who asks, some FHE schemes can operate in SIMD mode. Can your compiler support SIMD?
Oh yeah, great question. So our array types, essentially, if you compile with an integer scheme, this automatically batches and does the SIMD operations. Now, if you compile it with a binary scheme like TFHE, this will essentially compile it to an array of bits.
Okay, still have a couple more minutes for questions. Here's one from Ryan Wales. Was it difficult to define a common subset of HE library features in T2? Are you aware of any specific features that are available in some HE libraries but not in others that cannot be taken advantage of by T2?
Okay, another great question. Yeah, one thing that we don't do, and mostly because when we were writing this paper and developing the code, Concrete was under development, and TFHERS, these are two libraries from XAML, they do programmable bootstrapping. So our compiler right now, it does not support programmable bootstrapping, which would be a nice add-on. The problem is that if we allow, because we considered adding programmable bootstrapping, if we add this to the T2 language, then this will only compile to TFHERS, for instance. The other libraries do not support programmable bootstrapping right now, so it would be kind of unfair. So we would write a compiler just for TFHERS instead of all the libraries.
Okay, we still have a minute. We could take another question if there was one in the audience.
I think over there.
Oh, okay.
So does your compiler also look at different parameters for the different libraries?
We don't automate the parameterization, but for all our benchmarks and different input sizes, we have different parameter sets, which we have documented. And when you compile it, you can include a file that has the parameters. Now, if you come up with a new application, the best way to do this is to try to reuse some of our parameters. In case you want, to go deeper, you may have to modify them a bit. Yeah. Thanks.
Okay, let's thank the speaker again.
Okay, thank you.